All right, through the miracle of a modern age, we are back in part two. So we talked about like where we came from, which is transformations that ultimately prove we have these triangles that are either congruent or they're going to be similar. And so now we need to evolve that question past that point. And so let's talk about limitations on using transformations to do this. Because like a natural question to ask ourselves is, well, we do have this way to prove triangles are similar. You know, the essential question is how do we actually prove triangles are going to be similar or congruent. And so why not just use transformations the way we have been using it? Because it seems like that actually worked. Well, there's going to be some natural limitations on transformations, and this is going to be no surprise to anybody who's done it, because transformations are a very precise and studious study, and it takes a lot of like careful thought, and there's lots of places that you can mess it up. And so we should reasonably think about the limitations, especially right now after you've taken a test that frankly was a pretty tough test. One thing I would say about transformations, why maybe we don't want to keep using transformations to do this, is because it's so reliant on the grid. You have to use coordinate points, you have to use mappings, you need a cheat sheet, you have a rule, you have coordinate rules, you have formal rules, you have composite rules. You just have a lot to take care of. And because you're all kind of centered around having to do this on a grid, ultimately transformations are not going to be a way we want to do this or maybe want to approach it. I would add to that and kind of explain in detail that it is extremely tedious. And what I mean is there's a lot of slow steps you have to undergo to actually map a transformation. It's not easy. If you had trouble mapping transformations, particularly those last two problems on the written part of the test, you're in good company. Those were tough. Excuse me, those are really tough problems. And so like this whole idea of using transformations to prove similarity may not just be the best way to go. I would also argue that it's impractical. And so the idea of it's great, and one of the reasons why like the state of Missouri and the Columbia Public Schools wants you to know about transformations is because like it's an easy way to see you doing geometry. But in the end, I would argue this is not the way like actual geometry is done. Geometry translates to literally the study of the measurement of the earth. The geo means earth, ometry means a study of the measurement of. And so like biology is a study of the measurement of life, right? Geometry is a study of the measurement of the planet. Like this is not a way the planet is actually measured because there's no grids anywhere. It's not like you can go out to like the front of battle and there's all of a sudden this Cartesian coordinate grid with an origin and these perfectly formed shapes. And so it's nice to kind of evolve thinking, but it's not actually practical or even really modeling what we have so far. And this last one for me, I think is probably the biggest reason why transformations aren't great. You can't actually make any logical assumptions. It's so precise and so demanding that you need a ruler and you need these rules. Otherwise, you're not really doing a transformation, you're just approximating. But anybody who's like lived in the real world as long as you guys have know that that's just not the way the world works. Like sometimes it's okay to make like logical leaps or logical assumptions and still solve a problem really, really well. And so for all these combined reasons, I don't believe that this is actually the best way to do it. It is a way to do it, and it's a good step up from like just like guessing that things are congruent. But in the end, we have to do something else. Transformations examine the movement of the whole shape. And that's why we have those mapping lines. And so if transformations are obsessed with like the whole shape and how it moves to some other location, then that means we have to like stop and think of it as a whole shape. In fact, I would argue you have to think about it as excuse me, you have to think of it as the components of the shape, and we have to individually examine or inspect those. And so, like the big takeaway here is that we have to look at the corresponding components of two triangles or two shapes and have those guide our conversation about congruency. Now let's take a second here and just like make sure we're on the same page about this word right here. Now this is not the first time you talked about it in class. I'm certain it's not the first time you thought about it in mathematics, but just for the sake of the sake of the class and the good of the group, let's remember that corresponding basically means the same component or the same piece in two different objects. And there's lots of ways to kind of like explain corresponding or to analogize it. Recently, because hey, so the World Series just happened, a good way to think about corresponding would be a position on the same, I'm sorry, the same position on different teams. And so they're not the exact same person, but they play the same role on their respective teams. And so, like, the catcher for the Cardinals would be like Yadier Molina, and the catcher for like the Cubs is not Yadier Molina, but they serve the same role on both those teams. In terms of like triangles, corresponding means like the same general location for a side or angle. So like I could say like this angle right here that I'm marking would be corresponding to this angle here because they're both like in the bottom left of the triangle. I could also argue that these two sides currently being marked are corresponding because they're both kind of like the right side of the triangle. Like that's all I mean by corresponding. Now when I do say components, as a review from the front, I am talking about specifically sides and angles. Okay. And so, like the leap I'm asking you guys to make is one. Even though transformations have kind of worked up to this point, there's a lot of bad things about transformations, and it leaves a lot of space for mistakes, and honestly, just doesn't model the real world very well. And so, if transformations examine the whole entire shape, then the alternative, and this is really like the big guiding point. Like if you don't remember anything at all from this discussion, please remember this part of it. We have to like look at the triangle not as a whole shape, but as a sum of its individual parts. And I think that's going to give us a different way to approach congruency and similarity than we've seen before. Okay, and so here's a technical bit. Here's something that we have to figure out. And again, you're gonna have to draw these diagrams in. So pause freely here. We have two different like definitions that we need. One is going to be the definition of congruency, the other is going to be the definition of similarity. In other words, if we're going to be looking at the components, the parts, and inspecting and respecting those to prove congruency, what's the exact burden that we have to hit in order to actually have congruent shapes? Well, the burden we have to hit is simple for congruency. Two figures are congruent if and only if all their corresponding sides and angles are congruent. And so that leads us to something that we call our congruency statement. And so this is something typically either you're given to begin a problem or that you're eventually going to have to come up with yourself once you know the triangles themselves are congruent. But for the sake of this exercise, allow me to give you a congruency statement. Now there's two levels of congruency statement. There's a congruency statement for the whole triangle, and that's what we call like a corresponding parts list or a corresponding congruency statement. Given the two triangles below, if I want to show they're congruent, and again, there's that sign. I'll tell you that the triangle, AHJ, is going to be congruent, and please write this with me. AHJ is going to be congruent to PYL. Now, you saw me pause there for a second because I had to like make sure I was checking my notes, but also I'm looking at this diagram because the way I write the congruency statement matters a lot. In earnesty, it doesn't actually matter how you write the first part, but the second part has to match precisely. Here's the reason why. If I were to make a component list or like a corresponding list, let me change colors actually. Let me go blue. So if I were to make a corresponding parts list, the congruency statement actually tells me what's parts congruent to what. And so I'm going to do some marking here and change colors quite a bit, so please bear with me. But if I know that the A is listed first and the P is listed first, what that tells me is that the angle at A and the angle at P have to be congruent. So angle A has to be congruent to angle P. And I can use that congruency statement in a similar manner. H is listed second, Y is listed second, so the angle that occurs at H and the angle that occurs at Y would also be congruent, and I should mark it. So the angle at H congruent to the angle at Y. Now notice how I'm saying the angle at P and the angle at Y. The things I'm marking don't have a single letter designation, but since it's unambiguous what angle I'm talking about, it's okay to use one letter here. Following that logic, we see that J corresponds with L, ergo J angle corresponds with the angle at L. And that's going to be 3 of the 6 parts that are in the corresponding parts list. If you consider a triangle, it is 3 angles and 3 sides, and so this work demands that you label out everything. We can also use our congruency statement to help us with the side lengths. Side lengths are segments. Segments require 2 points to name, and so if we notice that AH is listed first and PY is listed first, we can conclude that AH and PY are indeed going to be corresponding. Now, visually on the triangle, that also makes sense if you consider AH, which I'll kind of highlight here, another brown line, is connects the one marked angle, the pink angle, with a two marked angle, the purple angle. This has to serve the same purpose. It connects the same two corresponding angles, pink for one, purple for two. And so we can add that to our list. In this case, it's side length. So we have AH side length congruent to YP side length. And so we're just kind of listing out all the congruent elements here. We can notice that HJ is listed second and YL is listed second. So HJ and YL are going to be congruent. So JH and LY. Okay? And keep in mind the order in which you list these segments doesn't actually matter because they're unidirectional. Finally, and this is kind of the weird one, we have AJ being listed first and third. PL is listed first and third. Therefore, those must also be corresponding if these triangles are indeed congruent. And so we have AJ congruent to LP. Okay? And so like this is a full definition of congruency. This is the burden you have to meet if you're going to prove triangles are congruent. You have to show, so you have to show this stuff. So must show that all the angles that are corresponding are congruent and all the side lengths that are corresponding are congruent. Now we're not going to talk right now about how we're going to actually show all that stuff, but that is a burden you have to meet. Now with similarity, because it involves a dilation, we have a slightly different definition. We can say that two figures, in this case triangles, are similar if and only if all their corresponding angles are congruent and all their corresponding sides have the same ratio. Now again, don't freak out about this term ratio. Ratio just means the K factor, or the scale factor. Okay. But it works kind of the same way. So let me first derive a similarity statement. Now notice here that symbols are going to be a little bit different. So we can say that PRQ is similar, and we're going to use a single tilde for that, a single squiggly. So PRQ is going to be similar to BCA. Okay. Now if we're going to write our corresponding list, which we should do because you're going to have to do it later anyway, so let's get good at this now. So the corresponding parts. Okay, we can again take right off of our statement. So P and B are listed first, and so those will be our first angles. So angle P is congruent to angle B, and even though remember this is a similar statement, the angles themselves have to be congruent. It says it right here. The angles are congruent. Okay, so P and B are going to be good. Let's move on. So R is listed second. C is listed second. So R and C, so angle R congruent to angle C. Okay, and that's like super messy, but that's a congruency symbol. I'm going to go back and change it. And then lastly, Q and A. So angle Q congruent to angle A. Okay, now let's talk about the side lengths. Now this is going to be different. And the reason why this is going to be different is because we're talking about ratios. In other words, the scale factor or the K factor. Now, we don't know what that is. And so if K factor and scale factor mean multiplication going one way, then deriving that has to be inverted, hence division. Keep in mind that ratios, and maybe we should make a little note here, keep in mind that ratios are like fractions, but can be inverted. And the actual term is reciprocated, but can be reciprocated, which just means flipped. And so that's why they have a role here, is because we're searching for a scale multiplication factor. Division's how we're going to do it. Now we'll approach this in a similar way. We'll notice that PR and BC are listed first. And so let's first locate PR, that's the bottom here, and BC, which is also the bottom. We have to write this as a ratio, which again is going to be like a fraction. Now we have to pick a direction. We either have to put big over small or small over big in terms of the triangles. Now it doesn't matter which you do, but you do have to be consistent. And so I'm going to start with a big triangle on top, small triangle on bottom. And so we're setting a ratio of B to S, and that should be equal to CB as a line segment, to RP which is also line segment. Now, I guess technically we should take the line segment off because we're talking about the side lengths themselves, which aren't the structure. And again, this is going to be the big triangle over the small triangle, and that has to match all the ratios. And so we have RQ listed second, CA listed second. RQ is right here, CA is right here. Now we don't have the same length, but we can write the same ratio. So big triangle AC over small triangle QR. And lastly, okay, we have PQ, which is this guy, and then AB, which is this guy. And so following our same ratio, we should look at AB being over PQ. Now, if these were numbers, we could actually run the division problem and confirm that all the K factors are the same. But for now, this is good enough to show what the full definition of similarity and the full definition of congruency look like. So again, pause the video, or before we go on to the next part, take an opportunity to write a reflection about what we've talked about so far. So in part two, we kind of examined why transformations, even though they would prove congruency or similarity, are somewhat limited. And we kind of identified transformations as focusing on the whole shape moving, because we never really talked about individual parts and how those change or don't change. We just saw it as a shape. But if we could take away transformations, we have to then look at the parts of the shape. And so the big movement here, the big takeaway, is that we have to start thinking these shapes as a set of corresponding components, a set of corresponding sides and angles. And if those are congruent, then we can and have the same ratio, then we can say something about congruency and similarity. That led us to two big definitions, and these are going to be the biggest definitions for us that we're always going to try to meet. So congruency, the definition is that all the corresponding sides and angles have to be congruent, which gives us a congruency statement and a corresponding parts list. For similarity, they're going to be similar if and only if the corresponding angles are congruent and all the corresponding sides have the same ratio, which turns out to be some kind of division problem that will ultimately give us the scale factor, the K factor. We have a similarity statement featuring the similarity symbol, which is a single tilde, but we can also have a corresponding parts list of the three angles and then the three sides and ratio. Okay? So one last part that's going to see us put this into action. So see you guys in a sec.